Good afternoon. This is Dennis Keene from XTD. We'll be starting the webinar in just a few minutes while people get into the wait room here. Should only be about 2 or 3 minutes. Thank you. Good afternoon. This is Dennis Keene. We're going to start the webinar now. I'd like to thank everyone for joining us. This is a part of a two-part webinar. We're going to have the second one is going to occur next week on Wednesday, also 12 noon Eastern Daylight Time. This webinar is PFAS properties and remedial options screening webinar. So we're going to present a number of topics associated with properties of PFAS that are relevant to remediation, and then also a broad overview associated with those properties and how they affect remediation. We're going to have two presenters today. Our first presenter is going to be Ellen Moyer from Green Environmental LLC. Ellen is an environmental engineer with over 35 years of professional experience. Dr. Moyer works on projects for federal agencies and Fortune 500 companies to clean up hazardous waste sites contaminated by a wide array of harmful chemicals. Ellen has an MS in environmental engineering, a PhD in civil engineering, and is a registered professional engineer. She's also authored numerous articles and 3 books. Our second presenter is going to be Mike Marley. He's president and co-founder of XTD Environmental. He has over 60 years of experience in environmental and civil engineering. He's been at the forefront of developing design and application protocols for things like soil vapor extraction, air sparging, and in-situ chemical oxidation. Mike is commonly used with private industry and regulatory agencies to conduct peer reviews and provide litigation support for national and internationally. So we're going to get going on the webinar now, and we'll start with the next slide there, please. So slide 2 here is just a quick agenda. Again, we're going to do the introduction, which has occurred. We're going to go over the properties, uses, and occurrence and concerns with PFAS. We're going to have the PFAS remedial option screening for source and plume areas, and then we're going to have a questions and answers section. So, overview, really quick. We're going to find new and fast-changing targets. You know, which PFAS, which cleanup levels, can we measure all PFAS? We're going to discuss those items. Some of the PFAS remediation challenges, right? Very low part per trillion cleanup levels, numerous PFAS chemicals are all being or needed or remediated. That's the question. Transformations versus destruction or mineralization, some of the things we'll talk about. The risk of making things worse or not remediating adequately. And then to help address these issues, collecting appropriate site characterization data and perform treatability and or pilot testing. So this next section is going to be for Ellen Moyer, so we're going to push her on the line here. And we should be all set to go in 1 second here. And
thanks, Dennett. Thanks a lot, Dennis. Next slide, please. Next slide, please.
There you go.
Great. Okay, so I'm going to lay the groundwork for the discussion of remedial options. So I'm really boiling down a lot of basic information to what we really just have to know for a remediation discussion. You could spend days talking about this stuff, so I'm just going to give the highlights. So basically, PFAS are per- and polyfluoroalkyl substances. These are a diverse class of synthetic chemicals not found in nature with at least one carbon-fluorine bond. Now, these bonds are extremely strong, so it takes a lot of energy to break them. It's a huge universe of chemicals, and there are about 6,000 identified so far, or believed to be about 6,000 so far. Next slide, please. So these are generally structured as carbon chains with attached fluorine atoms, usually 2 to 18 carbons in the backbone. The per species have all the carbons in the chain fully bonded to fluorine atoms. And these are the most desired manufactured chemicals. There are also a huge universe of poly species in which not all the carbons in the chain are fully bonded to fluorines. And most of these are unintended byproducts of manufacturing. And as we'll see a little later, many of these poly species are precursors and can transform into the per species. And then there are a variety of other atoms that can be incorporated into these molecules, including oxygen, hydrogen, sulfur, nitrogen, and quite a few others. Now, the two that are produced in the largest amounts in the U.S. and that we see most in the news are PFOA and PFAS. These are both perfluorinated, and they both are with 8 carbons. And you can see the diagram in the lower right shows the structure of PFOA, showing the head with oxygen, hydrogen, and carbon, and then the tail with fully fluorinated carbons. Now, with such a wide universe of chemicals, it's hard to generalize too much, but in general, based on what we know now, PFAS are generally water soluble, have low volatility, and information so far shows that they are resistant to biodegradation. A lot of the PFAS chemicals, their properties have not been studied, so there are a lot of questions out there, but the two that have been the best studied are PFOA and PFAS, and this slide summarizes some of their properties, and I added benzene as a column just so you could compare the physical chemical properties with those of benzene, which we're more familiar with. So the first thing to notice is the molecular weight. These are large, heavy chemicals, 4 or 5 times the size of benzene or more. They also have a high boiling point. So if you want to boil these things, you need to throw a lot of heat at them. Vapor pressure measures volatilization from pure product to the air phase. And you can see that they have very low vapor pressure, so they're going to want to stay in that pure product phase. Henry's law constant measures volatilization from the dissolved phase to the air phase. And again, the Henry's constants are very low compared to benzene, so they're not going to want to volatilize from water either. KOC, the organic carbon partitioning coefficient, is larger than that of benzene for both of these chemicals, indicating the potential for pretty good adsorption onto organic carbon. And lastly, solubility in water shows that PFOA and PFAS have on the same order of solubility as benzene. So they're going to readily dissolve in water. Mike is going to show how those chemicals relate to the remediation toolbox in the next section. PFAS are widely used in many products in our daily lives. They have really good advantages in that they resist heat, oil, grease, and water. And there are many situations where we want chemicals that do just that. And they've been used in industry and consumer products since about the 1950s. And the products often contain a mix of different carbon lengths and impurities. They're used to waterproof clothes, for example, with Scotchgard. They're used in non-stick cookware, such as Teflon-coated pans. They're used in takeout containers, wire insulation, paper and paints, firefighting foams, carpet, furniture. They're just really all over the place. Next slide, please. They're found in soil, water, air, wildlife, and humans, including the Arctic and the Antarctic. And a recent study in the U.S. found PFAS in 97% of the human blood samples analyzed. The situation with PFAS really came to light strongly as a result of Safe Drinking Water Act testing in 2013 to 2015, in which many public water systems in the United States were required to test for certain PFAS chemicals. And they were found in in 67 water supplies serving more than 16 million Americans in 33 states. These supplies had at least one sample at or above EPA drinking water health advisories. Because of the chemical properties I mentioned, there's a tendency to find PFAS in large dilute plumes. And there are a lot of difficulties with sampling due to cross-contamination. I'll get into this a little more in a minute. And there's also a lot of difficulty just analyzing these chemicals in the laboratory. And many PFAS are not detected by commercial labs. So there are a lot of concerns with PFAS, partly because of all the things we don't know yet. Most attention has been directed to the longer chain PFAS, such as PFOA and PFAS. They are persistent, they travel long distances, and they bioaccumulate. Potential health effects are increasingly being studied. So far, people are linking PFAS to problems with child development, including learning and behavior, decreased fertility, disrupted hormones, increased cholesterol, suppressed immune system, and increased cancer risk. Now, EPA has established health advisories for PFOA and PFAS. These health advisories are each 70 nanograms per liter, which is the same as parts per trillion. And that standard also applies to situations where you have both PFOA and PFAS. The combined concentration should not exceed 70 nanograms per liter. And this is for lifetime exposure from drinking water, and it's based on lab studies of effects on rats and mice, and also epidemiological studies of exposed human populations. Last I heard is that EPA has no plans to establish maximum contaminant levels that have the force of law behind them. EPA does, however, plan to develop regional screening levels for site cleanup that should help us figure out to what extent to clean up sites. Now, other requirements on PFAS vary incredibly widely. Some states and other countries are looking at more than just PFOA and PFAS and are developing their own standards and guidelines. And in the absence of federal MCLs, the state standards lack enforcement teeth, but the states are doing the best they can in the vacuum left by EPA. Now, analytical challenges are extreme. Part of the problem is that low detection limits are required because of the low concentrations of concern. We really need to see very small concentrations. And then cross-contamination during sampling, and then just deciding on which of the thousands of PFAS to quantify and analyze for. Some of these you really can't analyze for, at least in quantifying their concentration, because standards aren't available for creating calibration curves. And all this is going on in a fast-changing regulatory environment and fast-changing technology for analysis. The so-called standard method of analysis is method 537, and this is a drinking water method using liquid chromatography and mass spectrometry. And this was modified by a technical advisory, or updated, I should say, by technical advisory to deal with the fact that there are linear and branched isomers of certain PFAS chemicals. And because this is a drinking water method, it is used only for 14 designated compounds, and it is not to be modified. Next slide, please. So in response to the need to look for additional PFAS and to look in other media, laboratories are developing their own, quote, proprietary methods to be able to do these tests. And these methods are developing fast. And one piece of advice for analytical is to use a lab that has a lot of experience with PFAS analysis. Now, in addition to analyzing the PFAS directly, there are a few other analyses that can be helpful. And one is fluoride analysis. This can help you evaluate the extent of biological or chemical remediation that releases fluoride from PFAS. However, a drawback is that the detection limit is pretty high, so you can't see down to parts per trillion levels. Another analysis that can be useful is total fluorine, and this can help us locate PFAS plumes, or at least the hottest parts of the plumes, and it can be another line of evidence to verify that remediation is complete. But again, there's the drawback of detection limits that are higher than we might like. Now, the issue of transformation needs to be factored into site assessment and remediation. The PER species don't naturally transform, but the polys often can oxidize and turn into PERs, either by biotic or abiotic transformation, which usually involves polys being cleaved at a weak spot, such as a carbon that's not fully fluorinated. To get a handle on this, a new analysis has been developed called Totaloxidizable Precursors. Next slide, please. Basically, what they do is analyze a sample as is using one of the modified proprietary methods usually, and then they take a portion of the sample and oxidize it and then do that same test again. And the difference between the two results gives you quantification of total oxidizable precursors, though there's no speciation involved in that, but you can get a sense of how much is out there. I mentioned that sampling is a challenge because of all the PFAS that are in our daily products that we use. And there are different versions of what's recommended and not recommended. I like this slide from Alpha Analytical because they've done a lot of actual testing of leaching tests on sampling equipment to see which contain PFAS and which don't. So the column on the left is some field equipment and supplies that are okay, and then on the right, some things that are not okay. And you can see some things on the right are things that we use a lot in the field, like Teflon caps, Teflon tubing, waterproof field books, Post-it notes, Tyvek. You have to watch personal care products such as cosmetics and sunscreens and insecticides and even food packaging. So you have to be extremely careful, and it also illustrates how entrenched these chemicals are in our daily lives. So Mike is going to talk about remedial options now, and take it away, Mike.
All right, and this is Dennis again, just really quickly. If anyone has any questions for the end of the webinar, just please make sure you use the questions section on the control panel of the GoToWebinar screen there. And we'll make sure we get them answered towards the very end of the webinar. And here's Mike Marley.
Thanks, Dennis, and thanks, Alan, for that introduction. So what we're going to talk about now, the second part that we're going to talk about next week is going to get into more detail in the different remedial technologies with case studies. This one's more of a overview of, based on the physical chemical properties and the research that's been done, what technologies are most applicable for consideration for the treatment of the PFAS materials. I re-put up the slide that Alan had presented earlier, just to, again, highlight some of the things that Alan highlighted before. There's some, as a remedial engineer, when you're looking at the physical chemical properties for this slide, there's some things that jump out. Obviously, molecular weight means that the molecules themselves are of reasonable size, which would suggest that filtration methods would have applicability to be able to remove some of these PFAS materials from a groundwater stream. Again, to point out what Alan's got here, or presented here, was PFOA and PFAS. And as mentioned, the actual polyfluorinateds vary from like a carbon 2 up to a carbon 16. So there is going to be other PFAS materials that are much lighter molecular weight than that, and all have other properties that are not represented by PFOA and PFAS, and that comes into effect, and you'll see it in some of the slides we have today, but a lot of the slides we have next week with regard to some of the lesser carbon compounds may not be as well treated as the PFOA and PFAS with some of these remedial technologies. Vapor pressure, as Alan mentioned again, when you're talking about solid vapor extraction or something like that at ambient temperatures, obviously you're going to have limited success. And similar with Henry's law, because of the desire to remain in the water phase and not in the vapor phase, that's going to make like an air stripper be something that would be difficult to use. The KOC, again, points out that absorption technologies are worth considering for treatment of the PFOA or PFAS materials. So again, this slide sort of summarizes what you get from that physical chemical data as well as some what's in the literature. And again, so what pops out in red is that basically ambient temperature SVE, ambient temperature stripping are not expected to be effective. Obviously, if you increase temperatures, you can basically change those properties, physical chemical properties, to make them more amenable. For example, on 1,4-dioxane, which is not what we're talking about today, but basically the thermally enhanced SVE has been used to remove that, and it has a similarly very low Henry's coefficient. Because of the molecular weight and the KOC, again, absorption technologies and filtration technologies have got applicability. Also, Anel had mentioned about the molecules. They typically have a charged head and an uncharged body. The uncharged body is then, applicable for the absorption, but the charged head gives the potential for ion exchange. And when we talk about the resins that are being manufactured for the treatment of PFAS, they actually have dual functionality in that they have an exchange component and an absorption component, which gives them sort of like an advantage over just pure carbon, since you're dealing with two mechanisms for retarding the migration of the PFAS. Biodegradation, two components. When you hear about biodegradation, you really need to understand that there's two aspects to this. There's the transformation that occurs through biological processes of the polyfluorinated compounds, where low energy systems such as M&A basically can cleave off these non-fluorinated, these non-fluoride atoms, and basically transform these products. And as Alan pointed out, most of that transformation actually causes the polyfluorinated to convert to a perfluorinated compound. Currently, I have read some research on biodegradation, but the papers themselves weren't yet convincing with regard to, there was no formation of the fluoride that Alan had mentioned as an end product of total mineralization of the PFAS material. So at this moment, the belief is that biodegradation, standard biodegradation basically is unlikely to be effective at this time, but we thought that about the fluorinated compounds back in the 60s, 70s, and now we do biodegrade those. So I'll be interested to see as time goes on whether Mother Nature comes up with a solution to the PFAS as well. We got involved in the PFAS about 11 years ago when we were doing some screening level treatment technology evaluation for PFAS. And at that time, the one thing that we seen that showed promise was oxidative technologies. And there is a lot more work that has gone on since then at university levels and with practitioners on looking at oxidative and reductive technologies. The common theme where we have seen success with reduction of these PFAS materials has been higher energy type systems. And by that I mean typically reductive and oxidative radical species that are formed with some of these complex oxidative technologies, for example, alkaline activated persulfate or mixtures of different oxidants, but also other processes that basically involve oxidation or reduction, such as electrochemical processes, have shown abilities to mineralize or break down these PFAS materials into the elemental fluoride. Sonolysis, again, which is again an oxidative process with added sonar energy, basically is able to again input a high energy and basically degrade some of these PFAS materials. On the electrochemical side, actually the people that are using the resins have been using electrochemical processes to take the waste stream from the resins when they're being regenerated, which are highly concentrated in PFAS material, to actually regenerate on site through the use of electrochemical processes to destroy the PFAS material. So that's definitely one that there's a lot of interest on going on. Thermal processes, obviously when you get a concentrated stream from a carbon system or a reverse osmosis system, you've got a waste stream. And typically they are now being treated by thermal destruction, but the temperatures are in excess of about 1,000 degrees centigrade that are being used for that. Thermal desorption, where you're dealing with PFAS on soils and you want to remove them, soil washing thermal, these are processes that are being used. Some people are just basically deciding there's not much that can be done with them today, and I'd rather isolate them, so they're basically, excavating and in a secure landfill or a cell, basically isolating the PFAS from being able to leach into the underlying groundwater, or doing in situ stabilization processes. Again, they're isolation processes to prevent contact between the PFAS materials and the potential for it to leach to groundwater by isolating it. So these are some of the technologies that really come out of the physical chemical properties. The next few slides are going to talk a little more detail about some of those ones, the ones that are the most common. And basically filtration, let's talk about filtration. The molecules are large, but they're not that large, so processes like ultrafiltration aren't going to work very effectively. It takes nanofiltration. It takes basically the size of your filter screen to be smaller than the size of the molecules themselves. And these molecules are usually described in terms of, because they're so small, they're described in terms of daltons, which is basically the size of a carbon-12 atom. And you need to restrict them going through the filter media. And again, nanofiltration is the only sort of filtration process that is effective at the 90% plus level. Similar to reverse osmosis, the polymers that are used to create the sieving that goes on in the reverse osmosis process basically is again a very small size, and therefore again can be very effective at removing the PFAS materials. Again, none of these filtration technologies are destructive, so you're creating a concentrated waste stream that requires treatment, and again, typically they're being incinerated at high temperature, or again, in some cases now being used through electrochemical processes. You would need pre-treatment of your groundwater because these type of filtration systems are going to clog with other things that are in your groundwater, and so you do need a pre-treatment process. One process that's been used more in Europe is the example that I've seen is sort of like a typical filtration coagulation flocculation process. Perfluoride is one product that is being used. And again, it's not a destructive process, it's just knocking out a lot of the PFAS materials before going to a typical absorbent polishing with activated carbon or something similar. So these are the sort of technologies that are out there that are in use today for that. The other process that is most commonplace, again, non-destructive, is the absorption and the ion exchange processes that we discussed as a result of the physical-chemical processes. The most common go-to at the moment is obviously ex situ application of granular or powdered activated carbon. So it's a typical pump and treat system where they're collecting the waters before hitting a sensitive receptor, passing through an activated carbon system to remove the PFAS material, which you've seen from the physical-chemical properties. Absorption is definitely something that can work, and we'll talk about that more today and also next week. Biochar is another, carbon-based product, which is a combination of biomass and charcoal. Again, it's being researched as the absorption media, and preliminary results show it can be effective, but its absorptive capacity seems to be lower than some of the other carbon-based systems. One of the other things that you're starting to see cells out in the literature is the in situ injectable carbon-based systems, colloidal carbon. We'll talk a little more about that in a few slides from here. But again, the same process, they're carbon-based absorption processes. And again, the thing to remember is a non-destructive. And unlike a chlorinated solvent or a petroleum compound that may degrade in the subsurface while it's being retained on these carbon systems, there is no definitive evidence that the PFAS material are going to biologically degrade in the subsurface attached to these carbon-based systems. The other materials that are typically involve carbon but have other materials, absorbent materials, is rem-bound metria. These are a couple of examples of those, and they involve other absorption materials like aluminum hydroxides, clays. And part of that can be isolation because you're dealing with low permeability materials in some cases. Again, similar to the in-situ stabilization, you can be isolating the PFAS from contact with water. As I mentioned, synthetic resins are gaining a lot of traction. They are engineered, basically plastics that are engineered to basically have absorptive and ion exchange capabilities. And because they're engineered, typically their capacity is higher than it would be for a natural process or a natural system like carbon, but they're typically more expensive, and so a site-specific cost-benefit analysis needs to be done. And you'd have those two mechanisms, again, of ion exchange and absorption, which factor into their capacity for removal of the PFAS. Natural zeolites, which are mined here in the United States and other places throughout the world, are being considered for a lot of different things, and there's research and development going on to see, since they can be low cost, are they an alternative absorbent that could be considered and used. They also can be charged. They can be, by treatment, they can be charged like an ion exchange media, and that again is something that needs to be considered. The in situ, again, at this time, it's being used, but what we want to remember, and it's not that they aren't effective, but what we want to remember is when we stabilize something in situ that is not being destroyed, there's going to be questions that exist with regard to the longevity of that performance. Is there going to be a change in the geochemistry or conditions in the subsurface that might cause release of those compounds from an absorbent? That's just something you need to be thinking about. Is that going to be a problem for you? A little more on the activated carbon, since it's the most commonplace technology being used there. This is provided by Calgon, and I've seen a number of their presentations. But obviously, not all carbon is created equal. There's multiple sources of carbon, and they're not all going to have the same absorptive capacity. And also, the manufacturing process itself can also affect the evenness and the distribution of the absorption sites. And that has to be factored in the selection. I'll show you an example of that in a second. Obviously, it's very popular. It's very common, the most common remedial technology for PFAS at the moment. This next slide sort of shows you how the carbon source can affect its absorptive capacity. What we're looking at here is the PFAS, the sulfonate, being removed from a groundwater using different types of carbon. And what we have, the filter-absorbed carbons are the agglomerated carbons, which ones are used to maximize the surface and the type of surface and spaces within the carbon to maximize the absorptive capacity. And again, the green and the blue-purple are for coconut-based carbon systems. You can see the feed coming in at about 0.8 parts per billion or 800 parts per trillion, and you can see the 70 parts per trillion treatment. And you can see that in this particular test, that the filter-absorbed, the re-agglomerated carbon system is basically removing the PFAS to below the regulatory standards over tens of thousands of bed volumes, which is the vessel sort of size that is used, whereas the coconut system breaks through much quicker. So again, just illustrating that not all carbons are created equal, so you must consider what type you're going to use. And next, in part 2, we'll also present some on the differences between the absorption of the different carbon length PFAS material. This is a little more detail on the injectable carbons. There's a number of them available. Plume stop is the one that you most hear about in the industry. Again, it's a colloidal site, so it transports well within the subsurface. It's got that high surface area for absorption. So again, this is provided by Regenesis for the plume stop. I added the question marks because, again, I want to illustrate the point that these are going to be effective at absorbing PFAS. There's no question about that. The question is, and if you look at the circular figure where the top right corner, contaminant absorption to sites available on plume stop, any carbon, that's going to be the case. The next two are the things that are different for PFAS than they are for chlorinated or for petroleum. If you're dealing with chlorinated or petroleum compounds, the microbes will biodegrade the absorbed contaminants. That's pretty much known. And then that makes the absorption sites become more available for additional contaminants, basically regenerates the carbon in place. That will not happen with PFAS, or there is no definitive evidence to show that that will happen. And therefore, basically, you have a limited capacity for absorption, and you will not expect it to be regenerated. And then again, it's sitting there and it's basically the question mark again exists as to what happens over the long term. Rembind was mentioned earlier as a carbon-based absorptive type system, and you can see here that involves activated carbon, aluminum hydroxide, and other organic matter to basically act as absorbents or isolators of the PFAS material. And it's being used in Europe predominantly. I've seen a number of uses. And here's an example, and actually it's the European site where it was used for soils treatment of the PFAS material with different percentages of the Rembind added. And you can see the leachability of the particular compound is reduced. The PFAS materials is reduced. In this particular case, we're looking at PFOA and PFAS again. And it's reduced as a result of the binding absorption associated with an isolation associated with the addition of these products. The resins we've talked about here is just an illustration. Again, these are plastic-based. They're engineered with very small size, a lot of surface area similar to the carbon-based systems, but they also have an exchange capacity. And it's because of that capacity that you typically get, that the addition of the ion exchange capacity, that you typically get that dual functionality and therefore a higher capacity. It also means that when you're regenerating this product, if you were to regenerate with an ion exchange only, it would not be successful because you've got absorption you got to deal with. And if you tried to regenerate with absorption only, desorption, then basically you'd run into problems because it wouldn't deal with the ion exchange. So the regeneration process has to allow for both mechanisms to be effective in the desorption process. And as I mentioned, there's a lot of work going on with the chemical oxidation and also electrochemical processes to regenerate or to treat the waste streams that come out of these non-destructive processes. This is just an example showing you the difference between, for a 5-minute anti-bed contact time, and again, a 10-minute anti-bed contact time would give you a different extension on the horizontal axis, but a similar sort of graph. And this is shown for PFOA. And again, it shows you what you would expect, which is for the granular activated carbon process, you are getting treatment to below standards, but after a lesser number of bed volumes, so same reactor size, lesser number of bed volumes, you're going to basically have a higher capacity for the resin. As I mentioned earlier, the one in situ technology, and it can be used for ex situ as well, that is showing promise is the chemical oxidation processes, and to a lesser degree, reductive processes. There's been a number of bench studies and some limited palette studies over the last several years looking at partial or full destruction of PFAS materials. Again, they're typically focusing on the PFOA and PFAS, and this is one of the questions, again, that is arising for the oxidation processes is, we're focusing on a small subset of PFAS. How are we doing on the remainder of that? And again, I'm going to show you an example, or Dr. Ball is going to show you an example next week when we do the second one of how the process actually indirectly identified a lot of other PFAS material in the groundwater that wasn't analyzed or couldn't be analyzed for. And we'll talk about that next week. But the common theme, as I mentioned earlier, between these chemical processes is that it's not a simple process. It's typically a complex chemistry. And again, you get that with multiple oxidants or with activation of oxidants that basically is causing the development of a lot of oxidative radicals and also reductive radicals that are occurring. These combined together are having this sort of level of success. And again, even back 11 years ago when we done sort of preliminary screening, we've seen very good effectiveness, in particular in the PFOA type compounds, the carboxylic acid type compounds, and to a lesser degree in the sulfonates, but definitely some reduction of the sulfonates as well. There is some literature out there also showing you that if you change from ambient conditions, and obviously this is not something you're going to do very readily or cost effectively in situ, but basically at high temperature and pressure conditions, even a lesser oxidant such as permanganate, the lesser strength oxidant such as permanganate, basically under the right temperature pressure condition can be effective, and similar to the ZVI. Some of the work with ZVI under ambient conditions has not been very promising, but so far, but again, you change the environmental conditions to reduce pressure and temperature, obviously more doable, cost effectively in an above ground reactor, that can work also. And as Alan mentioned, the TOPE method was developed based on research by Dr. Sedlec at Berkeley on chemical oxidation for PFAS, and is used now as a precursor to treat precursors as a step in the analytical process. And to speak of Dr. Sedlec, there's some interesting things that he has done with the PFAS materials that illustrates some unusual behavior that needs to be known. And I've got a couple of slides on this, and basically, so here's his experiments looking at PFOA and treatment of PFOA with persulfate. And it's catalyzed in the fact that it's low pH, so it's likely to be iron catalyzed that happened in this particular case under natural materials. But it said it was an unbuffered system, pH dropped to about pH of 3. And you can see the persulfate's going away with time in the top left one. The most interesting one, I think, is the top right one. And what it's showing you is a couple of different things. On the left side is the red bar or red-brown bar is the PFOA. That's the initial compound that was introduced to this reactor system. And you can see it basically, it's there by itself. As you move in time towards the right, you're seeing two things. One is you're seeing the total destruction of the PFOA that is occurring. And the second thing that's very interesting, I think, is that you're seeing the production of the lesser carbon perfluorinated compounds. So it's going from a 8-carbon system to a 7,6,5,4 carbon system as it converts down and breaks down and finally goes away altogether. And you're seeing it going away altogether by the bottom right, where you're looking at basically the formation of fluoride. And you're basically, with the triangles, you're seeing the formation of that free fluoride occurring with the boxes, the red boxes being sort of the theoretical amount that would be as a total fluoride. So you're seeing basically the fluoride production, total mineralization, but you're seeing that step-by-step breakdown, similar to reductive dechlorination of the chlorinated solvents. You're seeing that breakdown to simpler compounds. The sulfonates, again, as I mentioned, our experience with those and the experience that Dr. Sedlec has also had is they're a little more difficult to break down fully. You can see again that you've got the PFAS that is being broken down, but not to the same degree as the PFOA under this particular process where it was persulfate only. Again, next week we will show you one where it was more complete destruction. The summary of Dr. Sedlec's work was basically that he had success with a persulfate and even peroxide, converting these polyfluorinated compounds into the perfluorinated compounds. Again, showing you that lower energy systems were working to break down to the carbon fluoride bond, and even going further than that with some of these compounds. He had more difficulty with the polysulfonate compounds, PFAS materials, and he also seen a relationship between alkalinity and the presence of chloride and the effectiveness of those compounds. So a very interesting study. If anybody's interested, let me know and we can get you some additional details or contact Dr. Sedlec directly. Turned over to Dennis to sort of summarize part one.
Certainly. So just to summarize what's been presented already, big issues here. Properties vary, but PFAS generally feature. There's a strong carbon-fluorine bond, generally very high solubility, low volatility, right? There is absorption potential, as was demonstrated by the case study that Mike presented. Also, general resistance to biodegradation, especially in the per form. Some of the challenges that we see are it's relatively a new issue that's come up. There's fast-changing rules, and also the technologies are still being evaluated as far as how to deal with these compounds. There's obviously numerous PFAS chemicals So you're dealing with a large suite of compounds potentially to deal with different properties potentially, low concentrations of concern, and also the transformation of precursors. And then just to summarize state of the practice, soil excavation encapsulation is a common methodology as far as dealing with these compounds. Groundwater extraction with granular carbon resins or filtration are very common now as far as dealing with these compounds. Development and use of other technologies is growing. And then really the key, we think is treatability or pallet studies or testing. These are not essentially developed remedial technologies that have a long history with them, so you really have to deal with each site as a case-by-case basis and understand what the design and engineering is for it. And that's pretty much the end of our webinar. Before we get to the question and answer period, I just want to remind everyone that next week is part 2 of the webinar, and that's on April 25th at noon. That goes into a bit more detail with respect to remediation of PFAS compounds and relies heavily on a number of case studies. The other item is we will send out an email with a link that has a recording of this webinar and also a copy of the slides that you can download if you'd like to have them for your records. And then also, as far as attendance goes, if you need attendance information as far as for CEUs, I can send out that information to you if you contact me, and I'll have a list of questions also that I can give to you. So just really quick, I think most of these questions are going to be directed at you, Mike. So the first one is, how do PFAS compare to PCBs with respect to properties and also remediation?
Yeah, that's a good question, basically, and I actually use that analogy when I'm talking on the treatment of PFAS from a technical, but also a sort of non-technical. It's almost like when we first were dealing with the PCBs, we're looking at this, $1 trillion type of issue, and we're facing something similar with the PFAS potentially. Again, as Ellen mentioned and Dennis reiterated, there's a lot of unknowns that we're dealing with in the PFAS world at the moment. We can't even analyze for a good majority of the compounds that are out there. We don't have toxicology information, so we don't even know what we should be treating and to what levels fully. And so again, this is something that we want to get a better handle on, or we need to get a better handle on, because as a remediation engineer, if I'm talking to a client and they're basically saying, well, what should I do? Well, the question is, I don't know. Right now, you have to question what you need to do because there's a lot of unknowns that are still out there. But the PCB is a good analogy. I think obviously PCBs are very highly retarded in the environment because of their properties. I don't think the PFAS are as highly retarded. Plus, I think the suite of PFAS materials cover a much wider range of physical chemical properties, and therefore, while there is conceptual similarities, I think there is going to be significant differences in the transport aspect of the PFAS versus what you're seeing for PCBs.
And then we have one other question right now, and then I think it might be better dealt with potentially just by direct contact, but do you have references essentially for the data on, or data for the oxidative processes for the PFAS at all? Do we have references that are made available to the attendees potentially?
Yeah, so we can pull together a list of the references, and again, we'll be talking about that in more detail, given some case studies next week, but we will pull together some references on the work that was done. Some of the work that was done that we mentioned, for example, the study that we done about 11 years ago, that's client confidential, but some of the other ones there are references available to them in literature out there, so we will pull that together and send it to the attendees.
Great. Well, thank you.
There's a couple of other ones.
Do I just read them for you?
Yeah, can I save the slides? We will be sending out a link that will give you access to the slides on our website, so that you can have those and do with them what you want. And a recording of the webinar and the slides, same thing.
Yeah.
The link that we sent you will have a link to, I think it's YouTube.
It'll be a link to our website, and that will direct you either to YouTube or also to download the slides, depending upon what you want.
Those will be available. Again, we thank you for attending. It's interesting, and I know when I attend and do presentations on this, the attendee list is huge.
All right, thank you very much, and have a good rest of the day, everyone.